things that we have seen last time. Namely, let me first remind you of this quantum mechanical example, because I was told that it was a little bit too fast concerning complex analysis. So let me recap a little bit what were the steps involved. So we said that this is Schrödinger equation, right? This is equivalent to Schrödinger equation. You just plug the wave function in Schrödinger equation. And in terms of this object P, which is called the quasi-momenta, this is Schrödinger equation. Now let me make a comment that if it was not for this wiggly term, this looked like classical mechanics, where I have kinetic energy plus potential energy equal to energy. Right? So it's really cool that Schrödinger equation that looks so different from classical mechanics, now it looks very much like classical mechanics plus a small term. So that's cute, right? And indeed, the classical limits corresponds to setting this term to 0, right? Where quantum mechanics becomes classical mechanics. Okay, now what is this function? This function is a function that close to each of the zeros of my wave function, and there are n of them for the nth excited state. It has a single pole with fixed residue, right? Now, when I integrate around a pole, I get 2 pi I, right? Do you agree? The residue of a pole is 2 pi I. So when I integrate around all poles, that's n times 2 pi I. Do you agree? Because that's just an integral around one pole, which gives me 2 pi I divide by 2 pi. The residue is h bar over I, so it gives me h bar, the contribution of one pole. And then the other pole gives me h bar more. So in the end, this integral here gives me n times h bar. Right? This is exact in quantum mechanics. So this result is exact. There's no approximation, nothing. Right? On the other hand, we had the classical limit. In the classical limit, we said, well, I can drop for sure this wiggly term. But then P becomes the classical momenta. Then it's just kinetic energy plus potential energy equal energy. So the kinetic energy tells me what the momentum is. And the momentum is just square root of this expression. And that's what P is. So that contour integral there is now well approximated by replacing P by this square root. Right? Before, I could not deform the contour. You know, contours in complex analysis I can deform at will, right? But I could not because of the poles. The poles were there and I could not just shrink it to 0. Or if you want, I can, but each time I pass by a pole, I pick h bar until it disappears. Here, I can also not deform, not because I have poles, but because I have this square root between A and B, which are the points where the energy minus the potential equal to 0. These are called turning points, because these are the points, if I put a classical particle, right, in some potential with some energy E, what the particle does is it goes here, it hits the wall, it comes back, it hits the wall, it comes back. So it's the points where the trajectories turn. They are called turning points. It's where the particle hits the wall and comes back. It's the point where the kinetic energy is equal to 0. It's just, huh? Sorry, where the potential energy is equal to the n. Okay, so those are the turning points. And therefore, this contour integral here around this cut is equal to nh bar. And here it should be approximately equal because I replaced P by the classical P. Okay. And this is just, as we said, above and below the square root, the function differs by a sign. So that's twice the integral from minus a to a of this square root. Let's just do an example. Let's do the harmonic oscillator, where the potential is omega m, omega square, m square, omega square, yeah. Omega square. So it's omega square, x square. And the turning points, when I equate this potential to the energy, are when x is equal to twice the energy divided by omega square, right? Twice the energy divided by omega square, divided by m as well. Square root of that. You agree? So that's the turning point, minus and plus. And then I have to do this integral. I rescale variables and I get this integral. This integral is just the area of half a circle. So this integral is pi over 2. So all in all, I get energy divided by omega. And energy divided by omega is equal to nh bar. So I get that energy is nh bar plus omega. Okay? And of course, we just missed the 1/2, but that's fine. That's quantum mechanics. This is the ground state energy. That's the small effect of quantum mechanics that tells me that the space are not just n times h bar. There is a h bar over 2 omega ground state shift. And if you remember, when we found the energy by studying the large x of this term was what gave me the n omega, and this one was where the 1/2 came from. So it makes perfect sense that we dropped it, so now we don't get the 1/2 anymore. Okay, so let me just make one more comment, which is that if I think of how many states are there until this energy, right? What I can draw, what we often draw, is say x and p. And for example, for the harmonic oscillator, I could draw the line of constant energy. That would be some ellipse. But for a given potential, it's some shape like this, but not exactly an ellipse, right? So that's this would be a line of constant energy. For the harmonic oscillator, it is just this plus p squared equal to E, so it's an ellipse. Right? And then what would we say? We would say that here inside, there could be many quantum states. At the quantum level, I cannot... at the quantum level, I cannot just put a continuum of states. And each state takes an area which is 2 pi h bar. So what this problem is saying is that the area inside, which is what this quantity computes, you see twice this ellipse here. So this would be the area of the top part. With the 2, it's the area of the full ellipse. It is just saying that inside, the number of states is quantized and is equal to nh bar. That's just some simple quantization. Okay, so anyway, this is just standard quantum mechanics. Now that we know one oscillator, we started to do many oscillators. We said I have a table, which is an array of oscillators. Okay? And these oscillators, they are parameterized by some position nx and ny. Thank you. Some nx and ny, so they make a vector n. And we said that xn is a function which defines some kind of height at site n. So we imagine that each atom of my table can be up and down. Right? But we could ask, why not just left-right? Why not, for example, motion in the plane, or why not both, and so on? And the answer is yes, you could do that. And in the homework, you are encouraged to play with variations of what we are going to do today. So try to do that. Do longitudinal rather than up and down, for example. Right? But here, just for simplicity, we chose height only, because then there's only one function per site. So it's instead of having 2, which are the dislocation in x and y. So it was just for simplicity. Right? Then we said that this xn, it's actually smarter to decompose it into Fourier and say that it's 1 over the length. This is a chosen normalization just to make our computations easier. Summation over momentum modes k, x k e to the I k n. And periodicity told us, after fixing some mistakes, that k was 2 pi over L times an integer that we can take to go from minus L over 2 to L over 2. And I think in the lecture, I missed this too. So if you fix your notes, I think I missed this too in the notes. Okay, and this was coming from periodicity. And then there was some reality condition. The fact that it is real was telling us that x of minus k is x conjugate of k. And then we started with our Hamiltonian, which was sum over the sides, the velocity just going up and down, velocity square over 2m, that's kinetic energy, plus m omega square over 2 potential energy. Each side has some force that wants it to be around 0, plus kappa over 2 sum over L, where L is up, down, right, and left, x n minus x n plus L square. And this was equal to the sum over Fourier momenta of absolute value of x k square times m, some omega effective for momentum k over 2 plus momentum for momentum k over 2, where this omega k square was our omega square plus 8 kappa over n sine square of kx over 2 plus sine square of ky over 2. And from there, we just compute the partition function, z. Z was just the product over all Fourier modes of the partition function for each mode. And the partition function for each mode was just the usual e to the minus beta omega k n plus 1/2 for the harmonic oscillator, which we computed. It's a geometric sum. Then we expanded at large temperatures. And therefore, this was approximately equal to exponential of summation over k of logarithm of 1 over beta omega k. In other words, product of the frequencies. And the beta dependence just becomes log of beta plus log of frequency. So the beta dependence was kind of simple. And therefore, z, log of z, was minus beta minus number of modes, which is L square, log of beta minus sum of log of omega k. And therefore, from here, we would get that my energy is just L square over beta, as we knew already from the first lecture. Now what we are going to do now is to think more carefully now about this table and try to understand its thermalization, right? But any question here so far? So what's the classical motion of this table? Well, classically, what happens is that each one just evolves according to its equation of motion, each side, right? So what are the equations of motion for this side? Okay, so now we study classical thermalization. And I warned you yesterday, and I'm going to remind you that it's not the naive version is not going to thermalize. And the reason is that these are just some free modes, right? The original Hamiltonian, it looks like the various sides are coupled, but that's not really true. They are really a bunch of independent oscillators. So whatever distribution I start, it continues there because they are just free. So there's no way they are going to change their distribution according to the various modes and thermalize. In other words, what we have is more like a drum. We hit and the waves just boing, 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 just move, and they don't start spreading into the various modes. So we'll have to help a little bit. But let's code as if this works, and then to add the nonlinear effects we need is going to be very easy. Okay, so what are these equations of motion? Right? So So this p square is just this momentum Pn, right, is just m times x dot at position n. So the equations of motion are just x dot dot plus omega square xn. So for each n, the first two terms is just the usual harmonic oscillator. Plus, okay, I'm going to write and then we see kappa sum over L of x n minus x n plus L. Okay. And this equal to 0. What we would have to do is solve these equations. What we want to do now is solve for all n which are in some lattice, let's say 0 to L or 1 to L. So it's a lattice of L sides. You see, closed set. Okay, with punch boundary conditions, right? We punch the table. That is, we say, for example, that here in a corner of the table, say this could be like L over 4, for example, in a quarter of the table, we say that here the starting positions at time t equals 0 are equal to 0, but the velocities, right, we punch it, so they start with some velocity at t equals 0, which could be some random number, something random, say between some value and some value. Right? So we hit, it's not uniform, it's some random value between two values. And all we want to do is start with a punch there, evolve this system of differential equations, and see if things become homogeneous and thermalized. Okay? So that's what we do today. So today we'll go to Mathematica, and that's what we are going to code. So you can just watch. I think it's maybe better. And just watch, and if you want, you can code as well, but I think I'll give you the notebook at the end, so you can then play with the notebook. Okay. This good? Can you read or? Okay. So first, okay. So let's add a title where we say punching the table. This will be like the time evolution. So here we will punch the table and see the table and see what happens. Okay. So we start defining what are our equations. And our equations, as we said, we have some x at some position ij at some time t, right? And we take two derivatives with respect to time, that's the double dot. Right? And then we say that the second derivative plus some omega square times x of I and t, I and j of t, right? That's just this term here, plus kappa times the summation over L, that can be down or up, And then we'll say here xij minus xi plus 1j, sorry, I plus lj at time t, at time t. This is left and right. And there is one more term for up and down. Clear?
Isn't it kappa over m?
Isn't it kappa over m? That's true. It's kappa over m here, right? Which is what I call kappa with curly. I don't feel like it. Yeah. So it's Mathematica kappa. Okay. And this is equal to 0. And there are a table of such equations where I goes up to L and J goes up to L. Well, but here you see that we have xi plus L. I plus L sometimes can leave the lattice, and J plus L could sometimes leave the lattice. So we have to put boundary conditions outside at the boundary of the table. So just because it's simpler, I will choose periodic boundary conditions. Okay? But again, the first example where I said that we had some choice, we chose this table of height, and now we are going to choose periodic boundary conditions. So here's a second thing that you could do differently. You could put that the x is 0 at the boundary of the table. That might be a more realistic table. So I choose a table with periodic boundary conditions here, because if the table is big, it should not matter. But of course, you are encouraged to do something else. So let's do it boundary conditions. So we say xij of t, if we are outside the table, which means if I is bigger than L or I is smaller or equal than 0, then I'm outside the table. Or if J is bigger than L or if J is smaller or equal than 0, right? So this means that I'm outside the table if either of these things happen. Then xij is just, I mod out. It is just mod of IL with offset 1 mod JL offset 1. And I have to say what L is. So let me say L, let's say 60. Okay? And let's say kappa equals 5. And let's choose some omega equal 2, for example. Okay? It's just some numbers so that we can evolve the equations. And right? And here we say this. So now if I say x, say 25, 35 of t, it's this. But if I put here 85, it is just 25, because 85 is 60 plus 25. Okay? And if I put here minus 25, it's 35, because I add 60 and I get 35. Okay? So now the table is periodic. Good? And then we have a table of equations. Okay? So Mathematica doesn't display them all because it's many equations. Right? So it's good. Okay, so these are the equations. What are the boundary conditions? Well, the boundary conditions, as we said, is the following. So let's say for each, we will do the boundary conditions for each position. Right? And as we said, we will have that x of I, j at 0 equal to 0. They start all at the same position, but not the derivative. So x of I, j prime at 0 is not, that one will not be 0. And we will say that if we are in a corner, so let's say if I is bigger than than 3L over 4, and j is bigger than 3L over 4, so that means the upper quarter, the upper corner, right? It's really a 16th of the box, right? This small box here. So if you are here, something will happen, otherwise 0, right? Otherwise it starts quiet. And what happens? We can have some punch with some strength. It's not perfect, but something between, say, 4 and 6. Okay, some random real. If, close, and then we flat. Okay, so this gives me some boundary. Oops. Okay, so this gives me false. Why false? Are you joking? Sorry, 1 second. What's this? False. Why false? I think I know what happens. Okay. So the problem was that x was not defined, but this x prime had been defined with equal, not with equal equal. So it was not a set of boundary conditions. Okay. So here we have a set of boundary conditions. So again, what we did is some random velocities here. You see, for example, this corner has velocity, initial velocity 4. This corner has initial velocity 5. So that's like you give a punch. So not all velocities are perfect. There is some. It's not totally perfect, but it's very good. What are the variables? So we need equations, boundary conditions, and variables. So variables are just the x, I, j of time. So these are just our variables. So we solve for this. We are solving this set of 3,000 coupled differential equations, right? So we have 3,600 differential equations, one for each of these x's. Okay. We want to thermalize it, so we want to wait some time. So let's say 500 seconds. Okay. So we solve. Okay. The solution is I just solve the equations with these boundary conditions with respect to these variables when time goes from 0 to the maximum time. Okay? And this one is just to remove some stupid bracket and this solve gives at the end. Okay? This cannot be used as a function. So flatten. I made a table. I have to flatten to be just a list, a vector, otherwise it's a matrix of equations. What is wrong here? Xij. This needs to be a list of equations and boundary conditions. Okay. X61 appears with no argument, so I forgot some.
You forgot the t in the first bunch. You have the if on xij of t when you mod out.
Good, thank you. Okay, and then we solve this. We solve this set of differential equations, right? So that's the solution, and it will take a few seconds to solve. So let's try to see what happens. Let me, where do I have this? I should have it somewhere, but I don't find it. So doesn't matter. I finished. Okay, so let's say we have our variables, right? And I want to prepare this to be plotted. So I want to say that x, I, j of t, let's say it goes to I, j, x, I, j of t, because then each point now is a coordinate and then a function, right? So it's perfect. And then I replace the solution right? And this is what I call to-plot of t, right? And then what I want to do list point plot 3D. So I want to plot to do a plot of this, of to plot at time t. I guess that's it. And then we can manipulate this t from 0 to 500 in steps of 1.
You're missing the hold on the t when you define the plot.
Yep. Good, thanks. No, I'm not. Here I am. Here I don't want a hold.
So on the left side, it should be without an underscore then, or no?
Ah, no. This is wrong. Ah, where is my mouse? Sorry, my computer is too slow. Where is this? There is a typo here. There is xijt, and I need to close the bracket after the j. You see? After I replace solution, I wrote ijt instead of ij of t. And now Mathematica doesn't like it, and now it's crashed, or what? Okay. Okay, so now this is taking some time because now it's a big list of things to plot. So if you see what is there to, now we can. Okay. And now we have our table. Let's see if this works. And then what we did was, so let's plot up to 100, say. So we started here, we gave some punch in that table, boom, 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 and then it starts propagating. And now this should be a thermal table. But it's a drum, as I said. You see? It's not reaching a thermal equilibrium, it's just vibrating wildly. It's by no means transporting energy into lower modes. Right? But it's not bad, right? It could be better, but it's not bad. So this is the time evolution of the position. So that's how the height evolves. Okay. So let's make it a bit better. So how do we make it a bit better? We add some inhomogeneity. We say, let's add some inhomogeneity, mu. And now let's add some inhomogeneity here, plus mu. And now instead of xij, we consider that we have xij cubed. Okay, and let me add it with a normalization that I'm adding in my file, such that I don't get surprises. So mu equal to 5, and I think I chose, yeah, like this, it's okay. Yeah. So this is a new term. Let me try to paint it in a different color, even though sometimes Mathematica doesn't like this. Red, okay, more or less. Okay. So it's there. By the way, is it too small? Should I increase a little bit, or it's okay? Do you want me to increase more, or it's okay? It's okay? Okay. So I'm adding a cubic term, which means that to the Hamiltonian I add a quartic term. And now this cubic term means that now it's not linear anymore. And because it's not linear anymore, I expect that the various modes start talking to each other. Right? So let's try. So I add this extra term. Right? And now we ask to solve, and it did. Why?
You didn't run the first thing. Like the boundary conditions where you define mu at the top, you didn't run that cell.
I added mu and I didn't run mu. Good. Thank you. And now I run. And while this runs, let's prepare an important part of this plot. Let me think. 1, 1, 0. I'm checking if the syntax is good. 1 sec. Need a break. Do I? Blue cylinder. Okay. Okay, so it finished. Oops. One. Yeah, I didn't. Okay, now it's perfect, right? Okay, good. And now we evolve. We start punching the table. Okay, these legs are huge. Then we cannot see. And then now the modes show the modes are really thermalizing. But let's remove the legs. So now this looks similar, right?
Yeah, you haven't evaluated 2 plot.
Ah, that's right. How doesn't it look right? And now that we run, let's see. So it starts. I hit it there. And you see that now it's really much more thermal. Okay. Okay, good. So that's not bad. So now it's thermalizing. Now there is the small problem that if I have a mu, we don't know how to compute because we computed without mu. So it's a bit annoying that we added this nonlinearity and we don't know how to compute with it. So so the idea, as I said before, is that we have our drum and we want to push it to hold it tight such that we create nonlinearities and then let it go. So what we want to do, we want to create some function, dial of t, right? That's going to be something like 1 minus, let's say that after 300 seconds, you turn it off. So let me show you. Right? So it's a function that, and then it turns off. Right? And what I'm going to do is I put this in homogeneity with dial of t. Okay? So it starts in homogeneity. And then for the first 300 seconds it's there to help thermalize, and then slowly I turn it off. And then it's like releasing. It's like at time 300 I release the drum, and now it should thermalize a usual drum. Okay, so let's do it. Let's thermalize, and then boundary conditions, this, and this. And then this will thermalize. Now, you see that this solution is, so first of all, I'm doing it, you had a course on Mathematica, right? So this syntax is okay, right? It's not going, you understand what I'm doing, right? Everything is clear. But if something is not clear concerning some syntax, let me know. Now, this is a replacement. It's a replacement rule that says that x11 goes to this function interpolation, because that's the output of the differential equation. x22 is this function interpolation. x33 is this function interpolation. So each of them is an interpolating function, that has all these dots between 0 and 500. So it's a huge amount of information. It's very slow to manipulate. So if our goal is to do this experiment and then start binning the energy in different places and making averages and so on, to work with this solution is very inefficient. So it's better to save once the history, right? And then just manipulate it. But for now, let me just show that I manipulate. Let's just see that this is still good. So this is the first 100 seconds. So it should be very similar to before. And it is indeed, of course. But if you want to see everything, we should put 500. So it goes. Here, 300 is when it's changing and nothing is happening. Now we are just turning it off and it continues to be thermal. Okay? So this will be a thermal system. Okay? That, as we will now see. Okay? So this is, if you want, the time evolution. And now we create a section about saving the evolution for easy manipulation. So the point is that I don't want to deal with this solution. Say, first solution is some interpolating function 0 to 500. And it is just very inefficient if I want to say plot the energy in some bin and so on, because I have to pick these huge interpolating functions and plug it into derivatives and so on. So it's easier to just save it before. And what I want to do, therefore, is to make a table of, say, of this form. So AB goes to X of AB of T. And I will do it for all A, all B, and integer T's. So I'll save the data at all integer T's, say. So let me see if this is how I want to save it. Is it? Yeah. So what I'll do the following. I'll say this is going to be some positions of T. It's going to be a table like this, you see, which just replaces 1, 1 by x1, 1, and so on. And then I replace this by solution. And then what I will do down here is say that all the positions, to save all the positions of T, not all the positions of T, because all the positions is all the positions. It's a story. It's just a table of these positions from 0 to 500 in units of 1, okay? Which I don't need because it's out by default. Okay, but I can put. Okay. So one by one, I just make a list of all the positions, and 500 is actually T max. So let's put like this, T max. Okay. So we compute this table of positions. Right? In fact, this is a table, but I want just a vector with 1, 1 goes whatever, so I can flatten it. And then I compute all the positions by making such table. So if you want all positions, if I ask for what are the dimensions of this, so it has 501 elements, which are the various times. And then each time I have a vector of 3,000 replacements, which are the various positions at that time. Do you agree? So that's it. Okay. And then I want to save it. So what I want to do is I'll say that I save it. So I'll say this goes to notebook. So let me first see that I saved the notebook in the right place. Yeah. This goes to say notebook directory joined with, say, in the folder data, we say positions.txt. Okay. And this saved, which means that if I have a new section now where I'll do plots, I can start saying L equals 60. And if I had not run the evolution, I would just say that all positions is equal. And I call this text file. And then I would not need to run the time evolution. I just import all the positions. So I go here and I import. Right? And now all positions, say the last element, is a list of where are the positions at the last time. Right? And now I could start the notebook here. I don't need to run any time evolution. We don't need to thermalize any table. We just start here with all positions. But we don't want just positions, right? We want positions, we want velocities, and we want energies. Velocities, and we want energies, right? And then we will call them all, right? We will save all positions, all velocities, all energies. And we will say this will be velocities, and this will be energies. Right? So what are all the velocities? It's x prime. And what are all the energies? The energies is 1/2 x prime square, right? Plus omega square yeah. Okay. Just to make, now I realize something silly. Okay. So let's say I want kappa equal 4, omega equal 1, just for comparison with my notation. Kappa equals 4 is good. Mu equals 5 is good, and omega equal 1. Yeah. So while we continue writing the notebook, I'll run this. It's just so that I will have the same results that I'm here. Okay, this goes to the velocity, and now let's continue to write here. So we have x ab square over 2 plus
Do you need a t?
I need a t, thank you. Yeah, please help me. This is not so easy to do. Plus some mu square over 4 x ab to the 4. Right? So that the derivative, the 4 kills the 4, and we get the term we added to the equations of motion. Plus kappa.
And do you also need the tangent function there?
Sorry?
Do you need the tangent function?
Great point. We should put dial t. Great point. Dial t. Right? And then we have kappa 2 sum over the neighbors L, that could be -1 or 1. And then we have x a b minus x a plus l b square plus, and then we shift b, and I forgot t everywhere. Okay? Do you agree? Please help me check. Tac, 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 tac. There is a mistake here. L takes values -1 and 1. By the way, here did I do it correctly? No, I did it wrong. L takes -1 and 1. It doesn't matter, right? If L is 0, I'm adding 0. So it's irrelevant. Okay. It's fine. Doesn't change anything. By the way, let's just see the outcome of thermalization now. It should be very similar to before. We punch it, it goes, and then it just thermalizes. Okay, so it's fine. And then here, this is what we want to avoid. So we save all positions. We save positions energies, and we'll save positions, all velocities. I just save the velocities. And all energies. I just save the energies. And the energy takes a bit longer, so it's nice to see where t is. So we can do just to see that it's going to finish. Okay. So this takes a little bit to evaluate. In the meantime, help me see if I have a mistake, but I don't think so. So let's save this. Okay, and now this is run. So we could save all velocities, we could save all positions. Let's save it again. And the energies takes a bit longer because it's a little bit more complicated function. So we put some progress indicators to see that how it's going.
Did you reevaluate the solutions?
Sorry?
Did you reevaluate the solutions before the part where the equations are solved again?
Yes. Yeah. This is 77, this is 80, 83. So yes, I did. Okay, so it's saving the energies. You see, it takes a little bit longer. And that illustrates why it's a good idea to save it, because it's a more complicated object. It's not just positions. You have to take all these derivatives and so on. So I think it's a smart idea to save it, because if you want to, say, manipulate the energy distribution across the table, which is better than the height, right? To see the temperature, what we want is the energy. It's better if we save it right now. So let's check, while we wait, let's see what we will do to check, say, energy conservation. So energy conservation, what we would say is we want to compute the total energy. So we have this energy at each side, so we want to sum over all these energies. So we could do the following. So we could take all energies. So this is the distribution of energies. For example, the last one, let me remind you. So the last one, it finished running. All energies, all velocities. Okay. So I could save into some text files. So just so you see, these are some text files that are somewhere here. Thermal table, data. And now it is saving some text files. And you see these positions, it's a file which has 60 megas. So that's a list of positions. And velocities is a list. Okay, energies are here. And it has 5 megas. It's because there is a problem, you see. It's not, these energies are not good. Okay, so it's good that we found it. We should debug it, but where is it? Here. Okay, so we screw this up. Sorry, what is wrong? We forgot some of t somewhere, I think. Let's check. So the -1 here, there is some x11 prime of 500. What's the problem? Why didn't she evaluate this? So velocities, it's the same problem, probably. Yeah, why isn't she evaluating this?
Perhaps you should try /dot for substitution. Usually sometimes helps.
Here? Oh, sorry. Let me just check. I mean, what's this? So this goes to x, to the top of b, a goes to b, b goes to b, flatten.
The solution variable actually contain info about velocities. Oh yeah.
Solution t from 0 to t max is 500. The problem. Oh, there's some issue with this derivative.
try substituting the solution first and then taking the derivative?
No, that will work. If I do derivative with respect to t here, it's fine. It's uneven. No? Sorry. So this works for sure, but this must work as well. Why isn't this working?
Solution to substitute small.
Let me see. So now I think I understand that it should not work, but in my notebook it works perfectly. So. But I agree with you that it's a bit suspicious why this should work. So what I want is the following. So solution 1. Right? I want to it like this. G of t goes to G. And now I remove the argument t, right? You see, and now if I have x, 1, 1 prime of t, and I replace this, it works. But I'm confused. I mean, why in my notebook it's working, but okay. So in solution, let's remove argument t from the functions. So we solve, and then we remove argument t. Because then we are saying that the function x11 is this, not x1 of t. Because when we put a derivative, we don't see that pattern, x11 of t, right? But to be honest, I'm quite confused why then it was working in my other node. But okay. But anyway, now this should work. We'll see. Yes.
In your solution, you have a cubic term.
Yes.
Your energies are, to the power 4.
Yes.
Is that what you want?
Yes. In the same way that here I have a quadratic term and then I have linear, right? I take derivative with respect to x to write equations of motion. Right? So quadratic is linear, and I put over 4 because the derivative, the 4 kills the 4, and I get x cubed. Right? Okay, so it finished. Let me just check that this is still working. Yeah, still good. Okay, sorry for this. And then we'll plug position, velocities, and energies. And we will save them. And then we can load them, and we could start here. Okay, so now let's suppose I want to check first energy conservation. So the simplest thing. So I can take all energies, say the last one, and let's see that it looks good. And this should look a replacement that says 1, 1 goes to this energy at site 1, 1. 1, 2 goes to energy at site 1, 2. 1, 3 goes to energy at site 1, 3, and so on at the last instance, right? So what I can do is that I can ask, make me a matrix with those entries, where 1, 1 is the position 1, 1 of the matrix, 1, 2 is position 1, 2, 1, 3 is position 1, 3, right? Because the energies come perfectly in that format. Okay. So let's see where she is. She's evaluating this. A bit nervous, but okay. I think it will work beautifully, but okay. We'll see. If not, I'll go to the notebook that I prepared where everything is working, the notebook that I have here. Okay. So this gives me a matrix, right? And I don't want to do this. This will give me a matrix, but what we want to do is really do this for any at all the times. So now this gives me the energies as matrices. So this gives me a list of matrices, each of which is a 60 by 60 matrix with the energy density at each side. Okay, good. So these are the energies as matrices. And if I want to consider for a snapshot what's the total energy, I just average over the lines, and then I average over the columns, and I apply it for each energy matrix. So I apply it for each energy matrix, so say the jth one, and I make a table where J goes from 1 to, say, 500. Okay? And this gives, for each matrix, I add up all columns and all lines, right? And I'm computing the average, so this will be the energy per site, right? This is going to be the energy per site, which is the inverse of the temperature. Because remember, we computed the temperature is right here. The temperature is the inverse of the energy per site, right? So this is basically equal to 1 over b. Okay, okay, good, good. I hope it worked. So I saved into some files. Now I'm loading the files. Of course, I don't need to because it's saved already. But what we want to see is that these are numbers now here. Okay, I'll abort because I don't care about this. Oops. But let's see that these are numbers. Please, please, please be numbers. Oof, okay. Why is it slow? I don't know. Fine. Okay, so all energies are also numbers. All velocities is slower than all energies. Why? Okay, anyway, we are not going to use velocity. So it's -1, -2. So these are how the various energies are counting from the end. And we could make it into a sparse array. So this is a matrix which is 60 by 60, where in each site it contains the energy. Right? We could do it, as we said, for all of them. Now this is a list of sparse arrays. And we could compute a table of the energy per site. And you see that it's pretty constant, right? So it's pretty constant and around 0.8. And then we inject the time dependence. So we did work on the system because we turned off the dial. So it's like we released the drum. So the energy did change, and then it's pretty constant again. Okay. Now, this is quite remarkable because this is impossible to do. At first, you always get a factor of 2 wrong in some interaction, and this plot would oscillate like crazy. So the fact that it's super smooth here and there, it's a sign that we did not get any factor of 2 wrong. For example, here I put kappa, and here in the energy, where is it? I put kappa over 4, right? And you can check carefully that this is the correct value, that with this action, this is where the equations of motion follow from. Okay, if I put kappa over 2 and I forget some value, immediately the energy will not be conserved. Okay, very good. So we see that we have the energies, and they are pretty conserved in time, right? And this could be our energy conservation. So we could plot this, right? We could say that in principle there could be some error bars because there could be some fluctuations, and the fluctuations would be of the form, say 1 over L over 2. Let me show you in a second what I mean by this, or minus. Okay. So this will give me an idea of what I expect. So I just added plus minus 1 over square root of n. And this would be what I expect if I take the energies for a quarter of the system. If I take a quarter of the system, when it thermalizes, each energy there in a quarter of the system should go to this middle value with some fluctuations, which are 1 over square root of the size. And the size is L squared, but a quarter of the system means the size is L over 2. So this gives me an idea of the oscillations I expect on the energy if I compute the total energy, not of the full system, which is totally conserved, but of a block, right? So let's do that. Let's consider the energy in the corners, okay? So let's define the energy in the corners. So this is energy conservation here. So let's call this energy conservation. It's the middle line, and the other two lines give me an estimate for the fluctuations, right? And now what do I want to do? I want to take these energy matrices, right? And I want to take the nth one, or the time number t1, and I want to take a block of size L, and I take all elements from L j minus 1 over 2 to L I minus 1 plus 1, where I would run from 1 to L over the size of the small l, so small l should be a multiple of L, oops, and j from 1 to L over L. So you see that I'm taking the first matrix, and then you see j is equal to 1 goes from 1 to, sorry, here I meant Lj, to L times j, right? So the difference between these two is, say, put j equals 1, it goes from 1 to L. And here, from this to Li. Right? So here, for each, at each time, I make a table in blocks. So if this L is L over 2, this can take value 1 or 2. If this L is L over 2, this takes value 1 or 2. So it's the 4 corners. And for each of them, I construct a matrix. Right? So now this is a list of matrices. And what I want to do is, again, compute the energy there. So I take average of lines, average of columns of this. And I do it for this I and j. And I do it for n from 1 to 500. And I make a table here. And this would be what we would call the energies in the 4 corners. Right? So let's see what this is. This energy in the 4 corners. We have to define small l. Small l is L over 2.
Is it T or N?
Good. T. L should be 2 if I want to divide into indeed. L should be 2. One second. No. L should be L over 2. Why 2? No, L should be L over 2. This is okay. Tac, tac. Sorry. From this element to this element. Okay? So this gives me, I'll flatten it. So you see that this gives me 4 elements, 4 elements, 4 elements, 4 elements. So this is the 4 corners at time 0, 4 corners at time 1, 4 corners at time 3. And you see, first corners, for example, all the energy is in the 1 corner. That's where we punch the table. Next step, most energy is in that corner as well. That's where we punch the table. Right? But at the end, if we go to the very end, now it's very much well distributed everywhere. Right? So that's what we expect. So what do we want to do here? We just list plot this. Right? And this is the energy in the 4 corners. And we ask to see the energy in the 4 corners together with energy conservation. Okay. Why not? So I want to transpose, because if I transpose, I get now energy in the first corner, and then energy in the second corner, and so on, right? So because this was a matrix 4 by 500, and if we want a list of things to plot, we want 500 by 4. Okay? Because we want a sequence of all the energies in quadrant 1, all the energies in quadrant 2. Okay? So I have to transpose first. Now I can list plot and see the energy is evolving. And here it is. So you see that the energy in one quadrant is very big. You don't even see it in this plot. So we can make plot range all. So this is where we punch the table. And then the other ones started warming up. And now they thermalized. And then we just decreased a bit. This was holding our drum. We were holding it. And then we let it go. And it decreased a little bit. And it continued with this fluctuation. Okay. So just to emphasize how important it is, so this is a beautiful plot. Let's do it again without inhomogeneity so that we see how it will not work if we don't put this term. So let's do it again. And we just need to run all this. And then we want to run the energies. Let's run just the energies. The rest we don't need. So let's run just the energies. And then we want to run all the energies. And then we want, after all the energies, we want to make it into matrices. And then we want energy conservation. And then we want the four corners. And then we want to move this down for comparison. But then we want to run this. Okay, so while this runs, maybe we could now try to let's discuss a little bit what kind of things now. We saw that the energy thermalizes, so the energy becomes 1/4 at each step. But what else could we compare now that we have this experiment, right? We have our experiment, so the energies are almost there. So actually I can wait. It's basically done. If I am right, it's still here. Okay. So we do have some time. Okay, good. So let's suppose I want to compute some quantity and ask, does it look like the system thermalized? Okay. So here is something we could compute. We have our table. And one thing we could study is what's the displacement, the average displacement. Right? So what we could compute is say, what's the correlation between a displacement here at position n and at position n plus m? This should be a function of this distance. And we could ask, what's the expectation, the correlation between x at position n and then at position n plus m? When m is 0, it's what's the average of x squared? What's the average of the displacement? When m is not 0, this is what is called the propagator. Okay, the propagator is this correlation, how things propagate from position n to position n plus m. So we can compute this quantity in thousands of ways. So, but let's compute it in the way that following what we did before in the lecture. What we say, this is 1 over L squared. We go to Fourier modes. And then let me do it by, let me say that we sum over K and K prime e to the I K n plus I K prime n plus m, right? And then expectation value of x hat k, x hat k prime, where all these k's and k primes have vectors. Okay, let's first check the plot that we got. So you see that this is what we get now. So we punch the table, and it's not really thermalizing, right? It's really like a drum. So there is a big music here, boom. And then it oscillates, boom. And it will oscillate, and boom. It is just it is just not thermalizing. Okay, so this is better. Right? So here thermalizes, here it doesn't thermalize. Now, let me make an important comment, because what I'm proposing as a homework for this week is for you to do some nice movie, whatever movie you want, to illustrate this thermalization. It could be any adaptation of what we are doing in the lecture. As I said, it could be, for example, changing boundary conditions and making it not periodic and understanding how everything works and how things bounce off the wall and the table warms. It could be changing the table, instead of being displacement, being longitudinal displacement and repeating the same game. It could be also trying to think of other ways of thermalizing. We did it by putting some inhomogeneity in the restoring force. But it could be that we put some nonlinearity in the force between particles. Instead of being a linear spring between the two particles, that could be the nonlinearity. So we could have inserted some force between the two particles that it's not xi minus xj squared, but xi minus xj to the 4. Right? We would put a nonlinearity there. I thought it should also work if you should put impurities in the lattice. You say, randomly, I erase some sides of my lattice. That should make it less exactly solvable and so on. So I tried removing it, didn't work. So you can try to see, maybe, I suspect that if you put impurities, the nonlinearity can be really, really small and it will thermalize, but you will still need a little bit of nonlinearity. I also tried to imagine that I have my table and I do some cuts on my table. So it's not random inhomogeneities, but I say that in my table, there are no connections in some big segments. Because then the waves cannot just move. It's like you have various rooms and they should start mixing more and maybe to thermalize. It also did not work. So, but you can play. And you can, and not only you can play, you can, for example, try thermalizing a table, thermalize another table with some different initial condition, and then join them and see the equilibration and see how the two temperatures become the same. So as you will see, the homework is pretty open-ended. It is just do some movie illustrating thermalization. Basically, the purpose of that movie is for you to play with this notebook and think of other things you could do and try to make some nice presentation illustrating this classical thermalization. Okay? But now that this finished, I don't like this. I don't like this without, so I want to put it back and run again. Sorry. I'll run this. And then I'll run this. And then we'll run this. Okay. Okay, good. Now we could check this computation here. So let's finish this computation. That gives me the average. So now I have k and k prime, right? But the modes are independent, right? So if k and k prime are not the same, it's the average position of an harmonic oscillator, but that's 0 because it can be positive or negative, right? So if k and k prime are not the same, it is just the product of two averages because they are decoupled. And then by symmetry, it's just 0 because x and minus x could be the same. So here, k and k prime need to be the same. More precisely, this is non-zero only if k prime is minus k. So only if k prime is minus k. And in that case, so only non-zero for k prime equal minus k. Yes?
Are you missing a sum over n?
I'm not, right? I'm just computing the average, n plus m, there's no sum. Sorry?
What's the average over then?
Sorry. This average here, this would be computing the average at some fixed temperature, beta. The computation that we were doing. And that's what we want to compare with. We want to say that our system, it looked like it converged. Let's see if it's computing, it's still computing the positions. It looks like it is converging toward a system with some effective temperature. So this correlation, if that's true, should correspond to the propagator at some fixed temperature that we are going to compute. Then we are going to plot and see if it works or not. Right? It's it's a non-trivial check. We measure some temperature and now we check the correlations on the material to see if it works. Right? So let's do it. So now they need to be the same, otherwise it's 0, right? Is this clear? Yeah.
Can it be that k prime is equal to k?
No. K prime really needs to be equal to minus k. So the Gaussian integral, that the final partition function contains absolute value of x squared, which is like xk times x minus k. So the average of xk, just xk would be, xk squared would be 0. Okay. So that's okay. So this is only non-zero for k prime equal to minus k. When k prime is equal to minus k, you see it had to be like that. Otherwise, it will be very strange what was going to happen. N dependence drops. K prime is minus k. So then this becomes just e to the minus I km, which makes sense. It only depends on the separation. It doesn't depend on n. Of course, if they were the same, it will depend on n. It will be totally strange that the average would depend on where we are. Only it matters is the separation between the 2 points, not where it is on the lattice, right? And therefore, the result is 1 over L squared sum over k e to the minus I k m expectation value of xk x minus k. Okay, and now there are many ways of computing this. This is just computation. This is just a computation of basically the computation of x squared in an harmonic oscillator. So I could go to creation and annihilation operators, a dagger a, and I could, for each harmonic oscillator, I could write x as a plus a dagger over square root of 2. And then this is just the cross term, a times a dagger is what matters. And I have to do a geometric sum of n e to the minus beta omega n, right? Rather than just a geometric sum. And that will give me this average. This is just the same as computing average of x squared in the harmonic oscillator. Or I could use the fact that I already computed the partition function. Okay, the computation finished, by the way. I could use the fact that I already computed the partition function and just do a Gaussian integration. So let's do it in that way because it's easier. So the expectation value of this x squared k that we are computing there it's just equal to, if I compute my partition function, I have integral dy y squared e to the minus beta m omega k squared over 2 y squared divided by the integral dy e to the minus beta m omega k squared over 2 y squared, right? Because you remember that that was the energy, so I'm computing an expectation value of x squared. The position x appears multiplying this term, right? The average of the momenta just drops. So this is what we would get. And if I compute this quantity, this is 1 over beta m omega k squared. Okay. So is this computation clear, how to do these Gaussian integrals? This was in yesterday's tutorial, right? So it is it totally straightforward, these integrals? It's just doing, so for example, if I rescale y to remove this part, I immediately see that it's proportional to this. The only thing I don't know is what number multiplies here, because that number will be an integral with y squared, e to the minus y squared, and so on. So all you would have to check is that that integral is 1/2. And that will explain why there is no 2 appearing here from rescaling y. Okay? So the fact that it's this times a number, right? Yes?
It's y the absolute value of xk. Like, that's why you're integrating.
Yeah, I'm computing the expectation value of the absolute of xk, x minus k. So it is just, which you can think it's the real part square plus imaginary part square. And what would appear here would be real part square, imaginary part square, and that's one way of thinking. Okay. So this would be the result, right? So in total, we see that, let me just write the final result. Yeah, let's write here. That the expectation of the x at position n times x at position n plus m, this expectation is equal to 1 over L square summation over k. Sorry. Summation over k e to the minus I k m divided by beta m and then omega, which was omega square plus 8 kappa with this curly kappa sine square of kx over 2 plus sine square of ky over 2. Sorry. Okay, m vector and m mass. This is the mass, this is the distance. Okay. So let's check. Let's check that that it is indeed converging towards this propagator. Okay. So what we want to do? Remember that, say, all positions, say the last one, 500, is this. It tells me position 1, 1, this is where the displacement is, 1, 2, this is where the displacement is, and so on. Right? So if I want to take position ij, I just do this, ij slash dots, and this gives me what's the displacement at position ij. And I want to multiply by the position at displacement I plus nx, j plus ny. And this gives me what is x at one position, x at another position. Right? Before, let me go up here because I forgot. So energy, so if I take the mean of these energies, right, we get this line, and this gives me the effective temperature. So let's do it. So if I take minus 1, so the last energy, so this beta effective is equal to 1 over this. Okay. So my effective temperature is 1.38. My effective beta. So my effective temperature was what was there before.
Don't you need L squared or something like that?
No, because this is it was L square over the total energy. But these are means already. No, temperatures should be in intensive quantities, right? They are not extensive, right? Good. So this is my effective temperature, 1.38. So we will need it because we will make a prediction where the beta that appears here is that effective temperature that we have to put here, right? So here we will put this 1.38. This m was 1. This omega was 1. This kappa was, I forgot, 5, I think. I forgot, let's see. Kappa was 4. Kappa was 4, omega was 1, m I didn't even put, so it's 1. And mu is nothing here because we turned it off and we would not know how to compute it with mu here, at least not today. I'll mention a little bit how we will do it if we wanted to compute with mu, and that's using what's called Feynman graphs, but that we will do next time. So let's continue computing this correlation between x at these two positions. So this is at one position how it would be. This could leave the lattice, so I would put here mod L. This could leave the lattice, so I would put here mod L. So now they are inside the lattice. And what I do is I go over all points. So I make a table of this, right? Where I go over all points, I, L, J, L, and let's say the propagator, let's say nx between minus 10 and 10. So some propagator minus L over 6 to L over 6. So we'll do some vicinity. And you will see why. The reason is because what's the expect when they become very far away, what we expect? We expect them their average, their correlation functions to decouple, right? It's like we are measuring fluctuations of a huge material. When I'm here or when I'm there, the things are not correlated. So it should go to the product of the two expectations, but each of them is 0 because of symmetry, right? X minus X symmetry. So it should decay as we separate the material. And because correlations should decay, considering L over 6 will already be more than enough. We will see that this object decays with distance. So L over 6 is more than enough. So ny, we can also go minus L over 6 to L over 6. And what else do I want to do? And I think that's it. So we want to do this table. And let's just check where are we in I and J. And this will be the at the end. So this is the last, at the last time where the positions are. Okay, so it's computing and it needs, the first entry needs to go to 60. So while we wait, let's see what we would do with this. So this is I goes from 1 to 60, J from 1 to 60, N from minus 10 to 10, and then N from minus 10 to 10. So it's so I want to take min of N, and that will give me, I will average in this way over I and J, and that will give me now a table of when I vary nx and ny. And this is, sorry, I'll abort because it's not what I want to do, sorry. So this gives me indeed, but I want to label well what is nx and ny. So I want to put here like this, nx, comma, ny, comma, the value, such that we can then list plot this easily.
ny?
nx, ny, and then this. Sorry, so let's run this. Hopefully this is correct. Positions, sorry, it's not correct. Positions minus 1, let's see, otherwise, now it looks good. So we take these averages, we flatten this partially, and this is to give me, I don't want a table here, I just want a sequence of position nx and ny and corresponding value of the fluctuation. Such then we can then go here and list plot 3D what we get. Let's say we do plot range all and plot style blue. And this will be a plot where as function of nx and ny, we will see these correlations decaying with distance. But in the meantime, this would be what we would call our experiment. Let's prepare our theory. And our theory is what we just computed. So our theory is 1 over, let's code this quickly because time is like Indiana Jones, right? So it's at 60. I have to finish coding before it reaches 60. And I'm talking. I shouldn't be talking. I should be typing. It's insane. What am I doing? Okay. 1 over beta effective sum of exponential of minus I nx Momenta, remember, by periodicity takes value 2 pi over L times some integer x. And then we have plus integer y, and y 2 pi over L, right? So that was our sum runs like this, where this n is the separation, divided by omega square plus, okay, now the propagator, let me write it like this, and then we'll see, 4 kappa. So in the normalization of the notebook, there is a factor of 2 compared to this 8. But here it's like this, 4 kappa. And then we have sine of this momenta. It was like this. And it was momentum over 2, right? So let's divide by 2, square, plus the same thing for y. And this integer was from minus L over 2 to L over 2, the Brillouin zone. And the integer in y was also from minus L over 2 to L over 2. And this was our theory. And then what we want to do is plot this. We want nx, ny, and then this sum. And we want to make a table over the same nx and ny, so that we can plot it. Okay. So we want to also monitor where is, say, nx and ny, to see that it's finishing soon. Then we want to do the same flatten that we do here and the same plot range. Okay, the flatten we plot range and plot style, because we want to put one on top of each other. This one better be a bit transparent so that we see the other one before. So let's make it transparent. So we say that it can be yellow instead of blue, and it can have some shiny. 20, for example, and opacity, it can be okay, slightly transparent. And this would be our theory. And then what we would like to do is show theory. Then what we would like to show is show theory on top of experiments. And now we just wait a little bit to see. But again, another comment concerning the exercise that you are encouraged to do. We are going to see the result of the propagator at the last time. We are using the last time, saying there it's thermal, right? And we considered at the last time, we did this average over positions by averaging over all the positions of my lattice. Where could the propagator be? But I could get more statistics easily. I could average over the last, say, 100 times where it was already very thermal, right? That would multiply my statistics by 100. So much better. It would give me much better statistics. The curves would be much nicer. But it would take 100 times more. And okay, you see, it's already taking a few minutes. But fine, if you have 1 hour, you just leave it running and go for coffee, right? But we could get many more statistics. We could even draw a movie of how this distribution is not at all what I'm going to draw now, and then it evolves over time as it thermalizes to the right one. And that's again another, I'm just giving you ideas for things that you could think of studying and playing with. Okay? So now it's almost done. And I'm already over time, so what I will do is I will give you the notebook where I will do one more thing. And let me just mention what that is, which is that we could also compute, say, take some big box and compute, you can see here in my notes, the distribution of energies in a box. So we take a box, like this box, and I move it around my lattice, a square, right, an imaginary square. I move it around and I compute the energy in each of these squares. And I could also average over time to have lots of data, and when you do, you get some beautiful histogram like this. Right? So that says most energies are here. You see that there are two curves here. Can you see? Why are the two curves? Because this one is computed once it thermalized with a nonlinear term. And then I turn off nonlinearity and the distribution moves. So the The higher one is the one at the very end. Okay, so it thermalized. But what should this curve be? Well, we know the density of states, right? It's just energy to the power of L squared minus 1. You computed yesterday in the tutorial. So you know what's the probability of finding a state between E and E plus delta E. You just integrate the density of states times the Boltzmann weight from E to E plus delta E. So with that, you can predict this full exact shape. Just integrating the density of states. And then you can see that it beautifully works, and it gives and it will just land exactly on top of this histogram. And that you can see in the notebooks that you will play with, how we can take a box. We did in the example, Alexandra and I, we did a 6x6 box moving around. And in this way, we compute some histograms and compare. Okay, so this finished. This will be our plot. So this is the propagator. You see that when at the origin, that's when the positions are the same. Then we get average of x squared. Otherwise, we get average of x times x at the neighbors. It's already smaller, and then smaller, 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 and it just decays. Right? And then we can compute our theory. Right? So this is our propagator. And you see that there are some fluctuations. These fluctuations would be much smaller if, as I said, you also average over time. Then this would smoothen out, and it would be a really beautiful smooth curve. I really encourage you to do. And now we have our theory here, what we expect. And then we have the comparison between the two. Okay, so we just have to wait till this finishes at 10. And I'll close these sections in the meantime. So this is what we did today. And it's almost there. And okay, and here is the comparison between the two. And you see that the yellow one is right on top of the blue one. You see, you can see it's not 100% perfect. There is some room for improvement, but if you remove I think if you average over time, these curves will be even closer and closer. But you see they are pretty close. And this is how the analytic propagator and the numerical, how this is working out. Okay? So the yellow one is this. Oops. So I'm comparing this curve with this curve, right? The analytic prediction and the theory. So let me just see if. So I have here. So this let me just see if this. But it will not work. Yeah, this will take some time. Let me see how long it will take. Okay, maybe while it runs, I just say. So here are the histograms, for example. And as I said, what is this? This is you take these energies, and you consider some bins, some box of size dl equals 6, and you consider the histogram, the energy distribution of these bins. And what should this be compared with? Let me show you here. Okay, let me change the zoom. This was the density of states you computed in the tutorial. So what do you expect? How many states are there? You integrate that density of states times the Boltzmann weight, properly normalized so that the integral is 1. And you integrate that at the effective temperature that we computed from alpha to alpha plus d alpha. You get some funny elliptic functions, whatever. Right? And then this you put on top of the curves that you get for the histograms, and you see that you get some nice match with this curve. Okay? And in fact, it even works before you turn off the inhomogeneities for reasons that I'm going to explain. I understood this morning why it works, so there is no exclamation mark. So, because you could be surprised, why did it work if you had the nonlinearities, which was the orange one? Because with the nonlinearities, we did not know how to compute. So why are the curves also working in that case? So the fact that it works for the blue one is obvious. The fact that it works for the yellow one looks a bit surprising, but we can explain why. And I just wanted to see if I had here, just some movies. I think this is what I wanted to show you. Oops, no. Sorry. I aborted. Beautiful. Okay. Anyway, so we will put this notebook online. This is a very nice movie. where you can just see the histogram distribution. All energies start localized at the top, right? So all energies are peaked. So the histogram starts with a big peak, and then over time it morphs until it morphs into these beautiful distributions. Right? So you will really see a histogram going from being something like this, like going up here and going down, and then morphing into this blue and orange curve as time goes. And that's quite cute because then those curves, on the other hand, agree perfect with a prediction that we would predict based on thermal equilibrium. Okay, so let me just make a comment that so the homework is basically, say, to do these movies of the histograms evolving and explaining why the histograms are evolving, or any computation that shows thermal equilibration, joining two tables, adding nonlinearities in other ways, trying to put vacancies and seeing how it would thermalize, studying rectangular tables rather than square tables, which allow you to check that you put an X and an Y in all the right positions, whatever you want. I mean, you can even make groups and decide that each group will do some different aspect of the problem, as you wish. And finally, we added some references to the wiki. Lauren just added, I sent Lauren. And next week, what we are going to start doing is something that mathematically is very different, but conceptually is not so different from what we are doing, which is to study thermalization in a quantum system. So what we are going to do next is start with some lattice and put some bosons in some corner of the lattice and let it evolve and see how the final evolution is that of a thermal system. Now, you see, quantum mechanics, everything is linear, right? Quantum mechanics, you just have a linear Schrodinger equation. So there is no nonlinearities, nothing. So the mechanism is a bit different. Conceptually, it's the same thing. It is just thermalization. We just start with some energy and things should thermalize. But the precise mechanism, how it works, this is what's called the eigenstate thermalization hypothesis, which is what we are going to discuss. And I added 4 papers to the wiki. If you want, you can read the introductions of those papers. Especially the introduction of the most recent ones, I think, are very clear. And what I would like to do, but I have first to code it myself to see how easy it is to do the exercise that one of the last paper does. Just start with these bosons, evolve them, and see thermalization. I think it's a very important and cute thing to know. And so that's what we are going to do next. Let me just see if this worked. Here is the histogram, you see? All energy is localized when we punch. And then as we move in time, they go here. And here they are, evolving in time. And at some point, we will release the drum. And when we release the drum, now, you see, the distribution moved a bit to the left. You see? And it goes here, 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 here. And when we average over time, we get these beautiful distributions. Okay, cool. So we'll put the notebook on the wiki. I'll see you next week.